Hello everyone, this talk is about approximate minimum directed spanning tree under congestion. This is a joint work with Christoph Lenzen. Let me start with the definition of directed spanning tree. Given a directed weighted graph and a node R, a directed spanning tree rooted at R is a subgraph which is acyclic and each node is reachable from the root, or equivalently it's a subgraph which is acyclic, and the in degree of each node is exactly 1 except for the root itself. We define the cost of this DST to be the sum over all individual edge weights, which makes it easy to define MDST problem, which asks for the DST with the minimum cost. 1 plus epsilon approximate 1 is also defined similarly, which asks for a DST that costs at most 1 plus epsilon higher than the optimal solution. Let me briefly define the models that we are working with today. The Congest model. In Congest model, we are given a network of n nodes or n processors, and they can communicate to each other if they have a direct edge between each other. We assume that these communication links has bandwidth of O of log n, which is sufficient enough for the nodes to transmit node IDs or similar things. The Congest model goes in synchronous rounds. Each round, nodes send messages, receive messages, and do local computation at zero cost, which means that they can even solve NP hard problems. We do not care about that kind of complexity here. We care about round complexity, which is the maximum number of rounds that it takes for an algorithm to finish. Initially, each node only knows about its incident edges in the graph, and depending on the problem that we're solving, we require the nodes to know their own part of the solution. For instance, our MDST problem here, we want each node to know which of its incident edges are inside the final MDST. We define congested clique as a variant of Congest model. The only difference here is that the communication graph is different than the underlying graph, and it is fully connected. Let me talk about the minimum directed spanning tree a little bit. The basic approach was due to Edmonds, Chulin, Liu, and Bach. Their solution goes in steps and gradually expand the solution to the whole graph. Depending on how you do these steps, you get different implementations with different running times. The efficient one is due to Gabo et al., which runs in O of m plus n log n, where m is the number of edges and n is the number of nodes. MDST has been studied extensively in a sequential setting, but in the distributed setting, it hasn't received enough attention, especially if you compare it to the special case in undirected graphs, which is basically an MST problem. It has received a lot of attention, a lot of works in both Congest and congested clique. But Fisher and Ashman is the first non-trivial attempt at a result in MDST problem in Congestion and congested clique. Their solution is based on a variant of Lovat's MDST for Piram model. Let me go into more details about what Fisher and Ashman did. They basically reduced the problem to the single source shortest path problem and proved that MDST can be solved in soft O of the running time of a single source shortest path algorithm on a graph of n nodes and diameter d in both congested and congested clique model, which means if we plug in the efficient single source shortest path algorithms, we get the following running times. They also conjectured that we can use 1 plus epsilon approximate single source shortest path to find 1 plus epsilon to the power of log n approximate MDST. Our main contribution is that we answer this positively and show that we indeed can do that. And we prove even a stronger result by showing that 1 plus epsilon approximate MD sinusoidal shortest path can be used for 1 plus epsilon approximate MDST, and we informally proved the following theorem. So if we plug in the most efficient approximate sinusoidal shortest path algorithm in congested clique, we get the following. Running time here, the small omega is the exponent of fast matrix multiplication. And in congest, if we plug in the fastest known approximate sinusoidal shortest path, we get the following, which is not a huge improvement comparing to the exact solution. And that's mainly because it's still an open problem whether one can do better regarding approximating sinusoidal shortest path. It's known that even approximating ST paths in undirected graphs or approximating MST requires soft omega of square root n plus d rounds. So there's a small gap there. But if we concentrate on special graphs, namely the graphs in which forward edges are at most lambda times heavier than the reversed edge, we get the following improvements in congest model, which is basically unconditionally tight for lambdas in log to the power of 1. And in congested clique, we get the following running time. I'm going to spend the next few minutes talking about how MDST is solved in sequential setting and the distributed settings that we talked about. And after that, I'm going to talk about the difficulties of our work and briefly state the high-level idea of the solution. So let's just start with the MDST. Let me go back to the definition of a DST. We know that each node is required to be reachable from the root, so that raises the question of how much do we need to spend for a node to be reachable from the root? So the simple question here is that we need to at least pay as much as the minimum incoming edge. So let's use that as a good starting point and ask each node to select one of its minimum incoming edges. If the resulting subgraph is a DST, then we are happy because we paid the bare minimum and we got our DST and it is the optimal one. But the problem is that sometimes we get these cycles in between, as you can see. So what do we do now? We can again use the same argument saying that this cycle needs to be connected to the root, so we have to pay at least as much as the minimum incoming edge of that cycle. To make it easier, we can actually contract this cycle to a node and pretend that we have a new graph and do the same process again. Also, to remember that we already have paid some amount for the selected edges. For instance, for this node, in the previous step, we selected this edge that costs A units. We remember that we have paid this, so we can actually show that by modifying the edge of other incoming edges, such as this one. We subtracted from the cost of this edge. So it's reflected in the next steps as well. So again, what we do is that we select the minimum incoming edge. If we get cycles, we contract cycles and continue doing this. If at some point the selected edges that we get from the selection process make a DST, we know that that DST is optimal for that contracted graph. For instance, look at this case here. We have two supernodes and assume that the selected edges are these orange edges. We know that this is optimal. Now the question is that how do we get an optimal solution for the uncontracted version? The answer is very simple. Since we already have paid for these edges inside the supernodes, we can choose any of them freely without any extra charge. So the simplest thing to do here is that for each node that don't have any incoming edge, for instance, this node here and this node here, we can select one of its incoming edges that we have selected previously to extend our MDST for the uncontracted version as well. This is the result. What would be the cost of the DST? Well, it would be sum over all the selected edges that we had throughout the process. Doing so in the distributed setting is not that helpful, and one can show that it's too sequential for our taste in the distributed settings. So what we want here is, instead of those steps, which are called Edmond steps, we want mega steps in which each component is guaranteed to get merged to another component at each mega step, which means that it is enough to do these mega steps of log n times to get exactly one component and finish the algorithm by constructing the MDST backwards. So let's take a look. Consider this example here. There are 4 components here. We concentrate on this component here. This is the cycle that has been contracted. So this is the new node with in degree 0. All the others have in degree exactly 1. We can actually apply the same argument we had previously. Again, this component, assuming that the root is not inside this component, it needs to be connected to the root. So we need to pay at least as much as the shortest incoming path to this component, and more specifically to this node over here, this zero-weight cycle. And if we follow the Edmond steps, that actually confirms our hypothesis here. As you can see, doing this is going to go to merge towards the shorter path. So we have 3 different options here. One costs 10 units, 7 units, and 100 units. And doing the Edmond steps, we gradually work our way towards the shortest path, which actually makes sense. It's following the same argument that we had previously. Well, how do we use this? Well, I think that the rest is pretty straightforward. We just need to find the shortest incoming path from outside. That's where we use the single source shortest path algorithm. And given that, we use all the edges from this shortest path in our MDST, and for the nodes inside this component, for all of those that have distance less than the cost of this shortest path, we also contract those as we have seen. This node contracted, so this one, not this one, or not this one. Well, this is the way that we do it in congested clique, which actually concludes this theorem from Fisher and Hossein. Okay, let's get into the approximate version. Let's define A to be Fisher-Hossein algorithm, and let's define A prime to be the exact same algorithm, except for changing the exact single source shortest path algorithm with a 1 plus epsilon approximate one. Then we claim that A prime actually computes a 1 plus epsilon approximate MDST. So the rest of the talk, we just analyze this algorithm. As you can see, there is no other changes in the algorithm. We need only pure analysis here. Well, it seems convenient enough. You're using, instead of a shortest path, you're using a 1 plus epsilon approximate one. So you are paying at most 1 plus epsilon higher than the optimal solution. But that's not the case, because as the components grow, the sequence of contractions are different, which makes components to grow in different directions by using different shortest paths, which means that the set of vertices that they have are different, which means that as your algorithm goes through in mega steps, forward through these mega steps, um, the vertex set of these components are different, which means different shortest path options are available. So it's very difficult to compare these to each other. Let's see an example here to make it clear. For example, consider this graph where this green edges cost exactly 1 unit and the orange ones weigh 1 plus epsilon unit. If we run the exact Fisher-Ashman algorithm here, in the first mega step, we get all the green edges, which is actually the MDST that we are looking for, and the algorithm ends. But if we run the approximate one, we might end up with these orange edges in the very first mega step. As you can see, the orange edges are 5 components, comparing it to what the exact solution does, which gets the whole solution in the first mega step. As you can see that the sequence of the contractions are very different here. And as I told you, the components are different and they go and grow in different directions, which means that they get different set of vertices, and this also influences the number of steps that it takes, and of course the balls that the nodes are contracting regarding that shortest path that we compute for them. So the bottom line is that relating these costs between the approximate run and the exact run is not clear and very difficult, in fact. So what's our approach here? Instead of running both exact and approximate algorithms on the graph G, we are going to modify G and get G star, and in a way that our approximate MDST on G computes exactly the same tree as A does on G star. So this is a key idea here. If we have that the optimal solution in G star is at most 1 plus epsilon higher than the optimal in G, we get that we get our approximate ratio. So what we want to prove here is that A and G star actually constructs the same DST as A prime does on G. And we're going to argue that both of them are contracting the same balls, so components at each step have the same set of vertices, and that's going to be helpful for the analysis here. So I want to note that it's not necessary, actually we don't need to compute this G star at all. We just need to show that such a thing exists. So there is no implementation here involved, and the algorithm is exactly what I told you before, and there's nothing more to add to that here. That's pure analysis. Okay, let's see how the construction of this modified graph works. So we go in step by step, mega step by mega step, and look at what the approximate algorithm is doing on the original graph, and gradually add gadgets to the modified graph to make sure that up to mega step I, both of the algorithms are making the same decisions, contracting the same balls and nodes. To begin with, we used U0, which is basically the original graph, but all the edges are stretched by a factor of 1 plus epsilon, which means that the optimal MDST in U0 is going to cost at most 1 plus epsilon times the optimal of G. And then, as we said, we want to add gadgets to current modified graph to make it to make sure that the following things happen. First of all, the gadget doesn't decrease the cost of MDST, increase the cost of MDST, and also it's consistent with the previous mega steps in the sense that when running the exact algorithm on this modified graph, we see that again, both of the algorithms are making the same decisions. And yeah, finally, the last modified graph would be our intended one. Let's see how these gadgets look like. So let's assume that we are at mega step I, and let's concentrate on this component over here. Let's define beta V to be the cost of incoming approximate shortest path in our approximate algorithm, the one that it finds in the current mega step, and just to see what this graph is going to look like after this mega step, it's going to contract a ball of all the nodes with distance up to a radius of beta V. So here, what we want to do is that we pick all these border edges U to U prime, such that U is outside the ball and U prime is inside the ball. And we're going to subdivide this edge and add these red edges to the graph with the respective cost. And for this node here that we created, it's a new node. We want this to be connected to the main node V by an edge of weight beta V, just to make sure that this node is inside the ball and will be contracted by the exact algorithm whenever we run it on this graph. So what we want here is to make sure that all the nodes inside the ball will remain inside the ball and get contracted by the exact algorithm. So we want to make sure that their distance to V has not changed, to just make sure that we add these edges from these nodes to V with weight beta V, and also well, we still need to talk a little bit more, because these nodes might still use these edges that we introduced here that actually, if you look closely to these might be negative. So we have to be more careful here. But the important thing here is that for all the nodes inside the ball, if they want to utilize these edges, they have to go outside the component and use one of these boundary nodes and use their respective edges to again come back inside and go to node V. But the cost of such a path is not going to be really helpful, considering the way that we chose the weight of these edges. So there are two possibilities here. If a node goes outside, use this edge here, and then this edge, or use this edge and then goes through another shorter path to V. But if you do the math for both cases, you see that the distance is not decreased, so we are fine with that regard. And for all the nodes outside the ball, we can do again the same sort of argument, but first we can note that for any node outside the component, it needs to go to one of the border nodes to use and utilize these edges. So again, we go into the same kind of situation that there are pros and cons in using these edges, and it never be the case that it decreases the distance. If we do the math, we get to that part. So we have a few ideas that are necessary to show that running A on G star, our modified graph constructs the same DST with the same weight as our approximate one on the original graph. There are a few other ideas and matters that need to get into consideration first, but I think that roughly shows how we can prove the following theorem and concludes the talk and paper. Thank you for your attention.